Okay, so here we are. It is going to be a little bit noisy in the background because we're outside of our house and we are going to do our beam testing today. What we have for you is 4 concrete beams, 2 unreinforced and 2 reinforced. The reinforcing is at this side, correct?
That's reinforced.
Yeah.
That one's, oh yeah, this is the bottom.
Yeah. We have our testing apparatus, which we will use a gauge, a force gauge, and a come-along or ratchet strap. And then over here we have 5 steel track pieces that we are going to test in various formats, and then a series of wood elements. And we'll talk about each of those as we go through it. So I'm going to move the camera around now and again. I'm just trying to position this so that you guys can see exactly what's happening here. And I'll come in and do close-ups. Now normally you guys would be sitting here enjoying this, or I'd be in the classroom, and I usually bring Dave along as my helper, for you guys to kind of see it firsthand. So we'll have to do, we'll ask the questions and answer for you, which are the questions you guys would normally answer. And what I love about this is sometimes you answer wrong, and that is almost even better because I think the takeaway is huge in that. So the very first one we're going to test is the concrete ones, and so Dave's just putting marks. We should have done that on the, oh no, the wood ones will be a little more obvious probably. So what we're going to do is we're going to treat it like a point load at the middle of, I believe they're 5 feet long. You guys are going to have a PDF in the module that you should be opening up now to take a look at. As we go through, we're going to check as close as we can what force they fail at. You guys have a diagram for what MF and VF, or M, because we're not factoring the loads, what M and V would be for a point load at the mid-span of a simply supported beam. We've created a simply supported beam condition here because these can splay just a little bit, and that gets us our roller at the other end. So we have vertical supports, so we have, it can't move up and down, it's not going to slide off, so it can't move back and forth, and it can't spin in space. So we have a stable setup, and the only way it can come apart is by failure. So Dave's prepping the first concrete one. What we did is we took some of the steel track that we're using to test the other ones and use them as forms. So we sprayed it with PAM, simple PAM, capped the ends, and then filled it with a self-leavening concrete. So it's a quick cure.
Self-leavening? Like bread?
I've been making too much bread. Self-leveling concrete so that it would set pretty fast. We've only done the concrete beams once before, and the unreinforced one broke before we could even get it on the testing apparatus. So we're hoping that with this concrete we kind of have a better mix that is really going to let us see what this looks like. So I will probably pick this up and bring it over to you guys on occasion. I have my safety glasses. Dave has built-in safety glasses with his regular glasses. And this is nice that we're doing it outside rather than in DA200, which can get a little bit noisy. I've always been scared someone's going to yell at me for doing this because I never really tell anyone what's going to happen. So Dave's getting it ready. We're being very careful because we don't want this to break even while we're just setting it up. Okay, so let's come in and take a close-up at the system. So I'm trying to do this so that I can see what I'm shooting and be as close to the microphone as I possibly can. So you can see that this gauge, oh, that's about as close as my camera can go, shows in pounds what the value is. So we're going to be writing it down in pounds. We know how to convert pounds to kilonewtons. So we'll be able to do that, no problem. So what do you think, Dave? Should we start testing our very first one?
We should. I'm excited for this unreinforced concrete.
You probably have to talk a little bit louder just because the mic is, there's so much background noise, it picks up the wind like crazy. So.
Okay, I'm excited for this unreinforced concrete. It's going to be brittle and dramatic. or what we refer to technically as catastrophic failure.
Woohoo! Okay. Whew. So, like 2 pounds, I'd say.
Something like
Something
that.
like 2
Maybe
pounds.
I'm not even going to bother with the ratchet next time.
Yeah, we could probably just use our hands for this one. So, let's write down first concrete unreinforced beam, practically 0, or 1 pound, I think we could possibly say.
Now, interestingly, we consider reinforced concrete to have unreinforced concrete to have 0 tensile strength.
Which we have this in bending, and so the bottom would fail in tension almost immediately, causing catastrophic failure.
And you can see from the failure line that it's a brittle failure. There's
Yep.
no
Once it starts,
deformation.
Once we hit the maximum stress at our extreme fiber, it fails all the way through because there is no yielding. All right, Dave, just use your brute strength. Go to the other side so we can see you. Don't even set up the testing apparatus.
Oh yeah? You want me to
just use your
Bruce Lee karate chop it?
Well, let's not break your hand or anything. I'm trying to, these things are so hard to level. Okay, go ahead, try it.
My finely calibrated arm, I've been working out. I should be able to do this. There we are.
Unreinforced concrete, 0 tensile capacity, which is so important in an element in bending because the bottom fiber is in bending. You guys remember, when we're bending something, top is in compression, bottom is in tension. So concrete, 0 tensile capacity, super crappy in bending. But if we put steel in that bottom layer of our beam, maybe we can make the steel do the tension work and the concrete do the compression work at the top.
Shannon, I am quite certain that this is going to be our most successful concrete beam test ever.
Our most successful concrete beam test ever. You heard it here first, folks. Dave thinks this is the best. Dave, I'm just gonna, before you do anything, I'm gonna pause this and see how our sound is. Okay, so I just checked the sound and it's not the super best, but it's pretty good. You guys can hear what we're saying, which is really the important part. So Dave now has lined up the first reinforced concrete beam to test. Here we go, Dave. I will try to bring the camera as close as I can to our scale. You can see that it's slightly uncalibrated, that we're starting.
Well, I've got a tiny bit of tension.
Tiny bit of tension. Okay, so we're starting at about 3 pounds. All right, let's start ratcheting, Dave.
We're hoping for a ductile response.
Yeah, we want. I'm gonna try to come over to this side because this thing spins a little bit. Don't get hurt, Bowick. Well, we're already doing better. Look at that. Pause for a second, Dave. Do you guys see that it is bending? It's bowed just a little bit. That means it is already working. We're at 20 pounds. We can see deformation. We've got some amount of yielding happening in it. So the steel is taking the tensile force at the bottom of the concrete. Let's pause for a second, Dave. Oh, stop. You can see, I want to get this as close as I can. We can see cracks beginning. Here, Dave, could you come hold this? You can see what's recording right there. I don't want to make them nauseous by looking at this, but right here, you can see cracks forming right here. So we're starting to get bending failure, or we're starting to get cracking in the bottom of this, but that doesn't mean it's failed yet. Cracking in concrete is okay. It just means that the steel is very much engaged right now.
No one imagines elastic response in concrete, but here we are, right?
And so if we unloaded this,
it would spring back.
It would spring back to its original shape.
Look at all the load it's taking.
We're at 100. Ooh! So I would say we got up to, that looked like we got up to about 100, just shy of 120 it looked like to me. And so you can see the reinforcing we used, we had fencing around our house, and it was welded wire mesh fencing, so we cut that apart and used it as the reinforcing as the bottom cord. So I'm going to write 120 pounds, approximately 120 pounds.
You know what's interesting, Shannon, is that this is over-reinforced. So if it's in concrete, when we normally design concrete, the rebar yields before the concrete fails.
That's our sweet spot for concrete, remember. We had the three options. We had balanced, over-reinforced, and under-reinforced. And under-reinforced is what we like because it makes all of the elements within it work all the way to their maximum. There's not a little tiniest bit of waste in the system.
So we didn't get the ductile response we were hoping for from this. We had a brittle concrete failure, which means that it was over-reinforced.
So we have bending in our steel, so it's yielded, but it hasn't failed. We haven't hit the maximum capacity of that steel.
Next year we'll have to use a smaller wire.
Yeah.
We use the 10 gauge.
Last time we did it, we couldn't get it to work properly, so we thought we needed the really heavy gauge of steel, so we used our thickest fencing element, but it turns out we were fine.
As engineers, one would think we would have had the ability to predict how much this.
When we're talking about elements these small, it's within the factor of safety of anything. It's almost, I'm waiting for you to, I'm holding this so you can slide it on. Yeah. We're within the element of like just unpredictability of it. A small flaw could make it have a vastly different result. So it's kind of one of the reasons why my firm, what I've done, is kind of interesting, because people always want engineers to design small-scale furniture elements, but we're using the building code, which is kind of really all about brute force. And so my goal is usually kind of trying to adapt the building code for things like this. It's kind of why your projects last term were about something just every day. So you didn't have to you could kind of figure it out on your own, what loads might go on it. You weren't trying to use building code loads necessarily. I'm sorry, Dave, I know you have a meeting at 2, and we started late. I hope I'm not going to make you ridiculously late, because this is too fun to not do.
Yeah.
Okay, we're prepping reinforced beam number 2. Let's see if we can beat our load of 120 pounds.
Okay, bring on the load slowly so we don't get any dynamic effect.
So we can see it bending already. Wait, stop. Train makes it really hard. Sorry, everyone. Train. It's a via. It'll be quick. There we go. All right, let's keep going. Let's hope a CN train doesn't go by. All right, we're at... The problem is you have to overdo it and then it undoes a little bit. So we've gotten to 70, 80. We've gotten all the way to 80. We've gotten all the way to 95. We've gotten all the way to 100. Oh, we're up! 115, almost the exact same spot. What's really nice about that is it is consistent. So the same system, same consistency. And that's what we're really looking for when we do these things. This video is really
we can
jumping
use
around.
these results to derive the compressive strength of the concrete.
We can. We now have 2 data points, people. We could work backwards from everything we know about reinforced concrete beams and figure out what compressive strength we had in that, because it failed to do the compression of the concrete. 2 data points, we'd have a pretty good correlation for that. Maybe if I don't sleep tonight, I could do that. Okay, should we move on to steel?
Yeah, we should.
Okay, very first steel beam. What we've done, no, maybe the one in the middle isn't the one to start with, yeah. I have them laid out in order going that way. All right. No. So this matches exactly what our concrete, this is the track we used to make our concrete beams. You guys can see that the underside has nothing and the top has a flange to it. So steel is great in tension, We don't need a lot of steel down here. And it tends to buckle in compression. So we have a little more steel up at the top. We have little pieces of wood in here just so we don't get some crazy local buckling due to where we apply the load. You can see right away that this has a lot of ductility to it, which it should. It's steel. We like ductility in our steel. Remember, that doesn't mean it's failed. It means that we have gone, well, this was just elastic, what I was doing right here. But ductility is when we go past the elastic zone and we get some permanent deformation in our element. So Dave will set this one up. We're going to do a few different beam setups. Sorry, I know someone complained that I drank a beer one time, but it is a gorgeous sunny day and my kids are with the nanny doing school, so I am going to have a light beverage. I know I had promised that we were going to have a family of ours where the 8-year-old is just in love with the idea of engineering, but with the new lockdown rules and not even having people outside, we thought it was inappropriate. And our town has actually just fared very well for COVID cases, has really kind of skyrocketed in the past week or so. So it's a different story here right now from what it was.
Okay, you ready?
It's kind of nice having Dave do this. I'm normally doing all of the grunt work and he's doing a lot of the talking. Okay, so what do you predict is going to happen on this one, Dave? What force do you think this one's going to fail at in pounds?
25.
25 pounds. Dave's thinking 25 pounds. I'm going to say 50. What kind of failure do you think it's going to be?
Well, it's a bit hard to say. It'll be some sort of thin plate buckling failure, but the tension flanges are down, so they're stable. So it won't be flanges.
It won't be local buckling of the flanges.
But it may actually be. They may be thin enough that the small compression zone in the flanges is enough to make them kick out.
All right. I think you're right. I think we're going to see local buckling just up close to the top, like we're going to, or maybe even the top cord. All right, so we're loading it up. We're at 50 already, so we well surpassed our predictions.
Wow. No buckling, it's nice and stable so far.
Lots of elastic deformation, possibly, so I can see that the deformation isn't consistent. Right there, we are starting to, at the point of loading, get failure. Dave is pointing to where we're actually seeing local buckling. I don't know if they can see that. It's hard to tell from the camera like this. I wish I could have the I'm going to move my laptop just a little bit closer, because this is all tied to it. Maybe I can get that a little bit closer. And our deformation here is a little bit steeper, like it's smooth, 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 and then there's a bit of a kink right here. So that's where we're going to see our failure. I think we're going to get 1.5 more ratchets out of it. We're sitting at 62 pounds now, which means we made it up to 70. Let's see what we get. All right. Oh, no, we've already failed. No more load is going on it. So stop for a second, Dave. I want to point out that there is no more load going on this system, but we have not had a catastrophic failure. That is the beautiful thing about steel. We can see it's failed. It can't take any more load. This is permanent deformation, but if somebody was standing under there, they'd look up and say, oh my God, that roof is coming down, and they'd get the heck out of Dodge, but there would be no loss of life.
That's what we call elastic, perfectly plastic behavior, right? Your load goes up linearly,
and then
it's flat, and you can keep adding deformation without a reduction or increase in load.
Well, we did, it stayed steady for a little bit. Now we're actually seeing a reduction in, oh no, you have it on, we do have a reduction in load. We do have a reduction in load. We're just going back and forth between 20 and 40 with deformation happening. But that was beautiful. That was beautiful failure right there. That was a really good result. So we got up to 70, I think, was what we got up to. So I'm going to write that down. Oops. I have a tendency to forget writing it down and have to yell out to the students what the numbers were. So 70 pounds. All right. Oh, we were going to do another one that same way because that's our calibration test.
Okay.
So I had them all sitting pretty much exactly the way they were supposed to be.
Yeah, I picked up the next one. I just didn't realize you wanted to do the same thing.
No, I mean I have them sitting
In the order.
not in the order, also in the
Oh, I see.
orientation that I want them tested as well. Okay, Dave's going to set this one up. Now this is the exact same test, so we would be hoping to see pretty much the exact same result. Might as well give you guys a tour while he's setting that up. Over there, that is Lake Ontario. There is a cul-de-sac between us and the water, but we're pretty lucky here. That weird little mouse house cottage thing is ours as well. I COVID purchased a, why is our, sorry guys, the camera is unhappy. Wonder if it's just the wires. This is what happens when you buy a crappy camera, I guess. We COVID purchased a trampoline. We have the pirate ship over here. Yes, that is full of sand. We have a casting mold for cast connects. On a project Blackwell specified, we turned into a clubhouse for the kids. And then COVID last year, what is going on? I built that play structure, and then we're slowly building that for the children. Okay. I hope this video is working properly. I will cry if it is a crappy recording. The hours that went into setting this up. Okay, guys, so we're hoping for the exact same result. We're at, oh, slow down, because we're at 60 right now. I can just see, yep, we're getting that same failure in the same spot at the top. We're at 70, and we can't take any more load than 70. So we're just kind of hitting it around 70, and then we've dropped down to 30, 40. Exact same result. And you're going to slip off the edge in about 2 seconds.
Oh, just like I did last time.
Yeah. So guys, that is fantastic. We're getting the same results. So I'm going to write that down. 70 pounds. Okay, so then this one we are going to do on its side. So this one, team, just for fun, we're going to treat it like a channel. We're actually going to do it on its side. So we're going to keep the solid edge upright. Are you all right? Are you going to be late?
I'm just going to let them know I'll be a little late.
I'm very sorry, because we still have a ton of things to test.
Yeah. Keep going.
Okay, so we're going to leave this edge open, similar to if it was a channel. So let's grab our testing apparatus. I recall this was all built just to hold the beam on its side like this. So if I also recall, this one has a tendency to try to twist on us. Now, you guys can already see that it kind of wants to wobble just a little bit here. Let's get this set up, and done this?
Want me to do it now that
Have I done it upside down?
Nope.
Yeah, you know, I have used these. What is going wrong? What is wrong with me?
every time, the first time is always weird.
Oh.
Oh, it is upside down.
It is upside down.
I do it.
Okay.
No, it's not.
All right. So look, guys, you can already see it's twisting. So much so that it's making our test piece want to twist as well.
Oh,
That's fine. So let's see what we get. What do you think's going to happen, Dave?
It's a characteristic of channels that shear center is outside, and so it always tends to rotate. So we could try preventing it from rotating and control that failure.
Oh, we've already got local buckling.
Oh, look at that.
You should see it on the top cord. It is wild.
Oh, here.
Yeah.
Crazy.
Yeah.
It doesn't take much.
So that is local buckling. We're at 30 kilonewtons. We haven't failed yet, but it's not going to take much more than that. Let's see what we get. Don't let it hit you in the head, Dave. We're at 50, and now we're yielding. So we've got our total failure going to slide right off. So we got up to 50 with the channel on its side. Now that's crazy because we normally say depth is better, but where the material was allowed for local buckling. We had a unrestrained flange edge on the top. Oh, a friggin' fly just bit me. It is April. What the heck, Bob? Ow. So we had a very flimsy flange edge. When it was on its side, or when it was downwards, it was the web was restrained by the flanges. And that is a big part of helping to prevent local buckling. So when we flipped that short edge onto its side, it was unrestrained at this edge, and it allowed for that quick local buckling response. Now this one, we have the web, or the solid part, at the bottom. So we have the channel in this position right here now. So we have a lot of steel in the tension zone, but almost no steel in the compression zone. Remember, steel in the compression zone tends to buckle very easily. And so the problems we had, do you know what, Dave? Just by putting the weight of the testing apparatus on, you guys can see that is bowed right here already. So we're already starting to see evidence of local failure just from the self-weight of this. We're at 5 pounds.
It's interesting that this section with the flanges up, the section properties, moment of inertia, and section modulus are identical to with the flanges down, and yet we'll see the difference in load capacity.
We got to 10 pounds, I'd say, just to do the ratcheting.
Was it even stronger than unreinforced concrete? Pretty close, right?
It got 5. I would say 5. It got more. Like, I would say the concrete failed at 1. You didn't even get to ratchet it once, but pretty darn close. So I am going to call that 10 pounds. What was the one when it was on its side? We got to 50, right?
Yeah.
See, I'm so bad at writing these down. I get so excited. Okay. So I want to.
What the heck is with your candy cane?
I want to show them this. I can't bring the camera up close enough, so I want to show them. So what the heck did I do with this? Well, you guys have seen that most of our failures have been local buckling, which is kind of a crappy way to have things fail. We go out of our way to make things class 1 and class 2 in steel so that we don't have to worry about local buckling. We just make those darn flanges and webs thick enough that local buckling isn't a problem. But considering I'm paying for all this, we couldn't find, and we couldn't get a testing apparatus robust enough to fail elements that were much bigger than this. This is what we have to work with. But what I've tried to do here is prevent local buckling without adding any extra strength to the system. So, if you can see here, I have filled it with spray foam insulation. That's to try to prevent it from buckling inwards. I have then wrapped it in tuck tape, and that's to try to prevent it from buckling outwards. The reason I left little tiny gaps in between is because I didn't want the consistency of the tuck tape to be like a reinforcing patch. So you guys remember the Kevlar strapping you could put on, like say under the gardener where concrete was spalling, for example. It can do a really good job at reinforcing, and I didn't want to, I just wanted to try to prevent local buckling. I didn't want to add any strength to the system. So that's why I didn't just wrap the heck out of this with the tuck tape. So first one, should we do downwards to be, we'll do the solid edge on top and the open edge at the bottom, the same way we did our first steel. What do you think, Dave?
Sound good?
So this is comparing. So they're both. Oh, sorry. So we're comparing this to our beams that got 70 pounds. So we want to see if preventing local buckling, which was our failure mode, will improve this. We might not even prevent local buckling, but we might delay local buckling by some amount. I wish we didn't have to work after this. This seems like a good day to, well, not go to the pub, but create fake pub outside. Here, I can hold that. If I'm just going to stand here, I might as well do something helpful.
Okay, are we ready?
All right, we're ready. So we're trying to beat 70 pounds here, folks. All right, let's see if my sad attempt at reinforcing for local buckling gives us more than 70. So we're at 50. Okay, we are just past 70. Just now, we're sticking it out at 70. Oh, we got up to 75. And now we won't go past 70. So you can see we've got the same failures. But look, we did a lot better. It seems to be just right here, which is where we had the failure before, but we also had lots of other warpings and bits happening. So we did slightly better, I'd say. So I'd say we got to 75 pounds.
It's interesting, we got a ductile buckling response, right?
Yeah.
Where we were able to keep adding load, but it wasn't yielding of steel.
Oh, look at you, muscle man.
Yeah.
You have been working out. All right, so I'd say we got up to 75 pounds. This one we're going to do.
Oh, the other way, right?
Well, we got to put the thing on anyway. We're going to do this one with the foam up. This is comparing to our 10-pound one, which almost instantly failed in local buckling. We put the weight of the gauge on, and it essentially failed in local buckling. So we're going to see if my attempt at local buckling reinforcement prevents or increases its capacity in any way. We put wood blocks in there so that the first year we did this, I didn't have wood blocks in there, and it would buckle right away just from the point load on the flanges. So the wood just gives us, it doesn't add any strength, but it helps stop it just from failing right away. Okay, so this one is to compare to the 10 pounds. I want to just, before you start to load it, we don't have that weird buckling that we already had right away on these flanges here. These are staying pretty good. A little bit right here, but not to the same extent when we did the one that didn't have the tape and the foam in it. Okay, let's see. Nah, We only got to just above 10 pounds, like maybe 11 pounds. So I'd still call this 10 pounds. So we still haven't nailed it. We don't have it right yet, Dave, for preventing local buckling. So, 10 pounds again, I'd say, folks.
In all of our tests, we have yet to generate a tension yielding in steel.
No, I know. It's hard to do. Especially with the products available at Home Depot that I can afford.
That we can break.
That we can break
with a ratchet strap.
With a ratchet strap, exactly. Okay, wait, let's show them what we're testing. All right, this is a piece of wood cut to the same dimensions to match our track. I want it, this one's gonna be a big train, I think. I might pause you guys, we'll see in just a minute. This one, I cut it to the same dimensions as the track. So it's a little bit wider than it is deep. That's just to have some consistency with this. And you guys will see that in the data sheet that you probably have open in front of you right now. So we'll set this up while the train goes by. Maybe put your volume down. Okay, the train's actually not so bad once the engine goes by. Sometimes they have 2 engines on these really long ones. So it might get loud again, but we're mostly okay now. Okay, so this, being wood, will also have a brittle failure. This one's usually the most fun. Students will often scream. Which is why I don't let anyone else touch this besides us.
Besides someone expendable?
Do you remember the year I was like 7 months pregnant with Duncan? And the time I was 7 months pregnant with Malcolm doing this. The students were very freaked out because I did it. We had a different system. We used bricks on a load platform until we built this wonderful apparatus. We actually used the weight of the bricks to gauge the system. Okay, so we are already at pretty much our highest load. We're at 110, which means you've gone up higher. All right, we've gone up to 150. We've gone up to 180. Let's stop for just a second here. So we're at 220 pounds. What does that mean, Dave?
1 kilonewton.
Yeah, pretty darn
we
close.
Also maxed out our scale.
Does this scale keep going around?
I don't think so.
Are you sure?
Just keep going.
I feel like it keeps going.
Well, let's see.
Let's keep going. So, but I want to talk about it for a second. Look at the amount of deformation we're seeing in this. So, let's just to give you guys a sense of the deformation in this. That's how much, oh my God, another train on the other track going the other direction. That's the CP one. So, if we undid this load right now, do you think the wood would go back to its original shape? Remember, permanent deformation only happens when something is ductile because there's yielding. Dave, is wood ductile?
Nope.
It is not. It is brittle, folks, which means if we unloaded this, it is still in the elastic zone and it would go back to its original shape. I'm going to leave.
It bounces.
Yeah, I don't want that to bonk you in the head. At least the broken one will break apart.
It'll be a lighter thing when it bonks you in the head.
So it keeps going past. So here's the thing. We'll be able to remember that we already did 225, 200.
Did you hear the cracking?
I heard cracking. Let's see if we can see anything happening under there. Okay, right here. I wonder if you guys probably can't see it. I'm going to try to.
And what you can't see is that there's a knot on this side.
There's a knot right here. You can see it all the way through. And sure enough, right here, the fibers are just starting to peel away a little bit. So we're about to get a tensile failure in wood, and we are, let's take a look at our scale here. Well, we're at 15 pounds, meaning we've gone past 225. We're getting there. It's not registering the amount anymore. Oh, we're Dave, our whole apparatus is moving that way. We've racked our apparatus. But you can see, I want to show them this. My gloves are caught in this. You can see this big crack right here. So we have failure.
It's perp to grain failure too, which is interesting.
That's
right?
not the most normal failure, but this is happening because of the knot. So essentially what's happening here is this is peeled away, and it's like this isn't part of the beam anymore, and we're left with this depth of beam right now. We're failing our metal brackets.
Mm-hmm.
I wonder if we should unload this one.
If you want and not wait for it to fail. No, let's fill it.
All
We
right.
can always straighten it. I've got that call at 2:30, so.
All right, there we go. Pretty good failure now. Oh, there we go.
So what I find interesting with wood is that in bending in wood, the principal stress is horizontal, tension in the bottom, compression in the top, just like everything else. Wood is so strong parallel to grain and so weak perpendicular to grain that even though the stress is parallel to grain, the failure is a perpendicular to grain failure.
Look at this.
Oh yeah, except there is some parallel to grain.
Yeah.
So you get the various layers of grain delaminating relative to each other, and it often starts at a knot, and at the knot the grain goes around the knot. So what had been parallel to grain has now a slightly perpendicular component. So, nice failure.
We have a second one like that. Do we want to do it?
Yeah, we do.
So we got up to, I would say, the 230 plus 10, I think.
Now this one we're orienting the other way though, right? Of course, we'll never get
No, we won't get it to break, so we're just not even going to do the one on the other orientation.
Or at least it'll be off the scale, so why bother? Right?
Yeah.
I wonder if we have WSIB coverage for this.
So you switched your call to 230? You're awesome, thank you. Let's Okay, so this one is just the exact same. We're doing the exact same thing. The reason I like to do two, especially of this one, is because wood is so susceptible to knots. We saw that the failure on that last one, you did turn it to the strong side.
Oh, I did?
Yeah. Hold on, let me read this. Okay, I want to just see, we have some small knots here. Doesn't look like we have any major knots on this one. It'll be interesting to see how this one performs compared to the last one. Yeah, it is funny that we have that
Yeah,
U-bolt.
what's that shackle doing?
Why did we do that?
Okay.
Seemed smart at the time, I'm sure. Okay, we've got loads of room to go, so. Ooh, got nice deformation happening. Okay, we're already up almost to where we were last time. So we're at 115. 120. Whew! That is what I was looking for.
Yeah, that's the good stuff right there.
Yeah. So that one I'd say was our 230 plus 15.
So that was really close, wasn't it?
Yep, very consistent with each other. Although this one had less of a slow failure and more of that brittle kind of pop that we would expect for wood failure. We don't like to get near that at all. We like to make sure that never happens with wood. Okay, so the next one, I have taken that same piece of wood and ripped it down the middle. So it's two squares like this. So it's the same shape, but you can see that it is two pieces of wood like this going together.
Now I'm just going to say that there is the thickness of a saw blade cut out of this, which would reduce the capacity by 1/15, which is 8%. No,
Let's get
6 2/3%.
Let's get our scale on there first. I was noticing, I forgot about that this one was thinner.
So I think we're going to fail at 200 pounds on this one.
Dave, making the prediction.
The intent was that it would be identical in dimension, but
We're not skilled carpenters. Okay, so you guys remember your lessons about what shape properties do and making things composite versus non-composite. This is two elements side by side making the same shape as the whole. What do you think, forgetting that adjustment for a 1/15, what do you think would happen to this? Should it act the same or different than the solid piece? John David, you're our audience.
I'm going to say that since the joint is vertical, it doesn't rely on shear transfer along a vertical joint. I'm going to say it's the same, Shannon.
All right, Dave, I think you are correct. It is going to stay pretty much the same. Now, we do have slightly less area because we cut out that saw blade length, so we're expecting failure somewhere around 200 to 220 pounds.
And it's still, even though it's oriented vertically, they're still stocky enough that I'm not seeing I'm not expecting a stability failure.
All right. We are at 180. Oh, we're getting.
We did get a stability
We did
failure.
get a stability failure, but that's our fault because of this.
Right. Interesting. So rollover buckling, which is why we put blocking between joists.
So if you guys see here, there was just a little bit of a gap right here, and it was just enough to allow it to twist.
Summer in the suburbs, Shannon.
No, that's our neighbor's generator. It's Wednesday at 2 p.m.
Oh my God.
That'll run for 2 minutes. I should probably... I think you guys can hear us over the generator. So what ended up happening there is because we had a little bit of space at the side, it allowed it to roll over at the ends. So it wasn't about the middle, it was that the ends rolled over. If you guys remember, we didn't have to worry about local buckling, or we didn't have to worry about lateral torsional buckling for wood if there was certain criteria that were given. And one of them was that we provide blocking at the ends of the elements so that we couldn't get rollover. So you will see if you're ever on a job site with wood, look for blocking everywhere. All the ends, often at the middle of bending elements, and that just means you cut little bits and wedge them in, which is exactly what Dave is doing right now. He is taking shims and using them to prevent end rollover of our elements. Okay, I think he's getting one more shim. one person didn't get your message. They're saying they're in the Zoom call right now. Okay, so we're taking that same beam and we've provided shims to try to prevent local rollover buckling, and we are at 200 and some pounds. There we go. 210, or sorry, the 230 plus 10 pounds. Exact same. So we ended up with the exact same failure. So I'm going to say 230 plus 10. So Dave is just going to send a text message, and I'm going to get the next beam. So now what I want to do is show you, or start talking about composite versus non-composite. So what I have here is one element of the beam where I've taken the hole, but I've cut it in half lengthwise. So we have half of the depth, but the exact same width. And then we're going to do one where we stack two of these on top of each other. And then we're going to do one where we stack two on top of each other, but laminate them together. So let's get this one set up. Failing it by actually pulling it off the ends before we ever even fail it, because its ability to deflect has gone up much more as a much greater ratio to its decrease in strength. So its decrease in stiffness is greater than its decrease in strength. And so we actually, if I recall from past years, ended up sliding it off the ends. We started to try to build some extra into the ends so that doesn't happen.
Shannon, can I ask, what is the technical definition of springy?
Springy? Oh, springy means boing, 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 in the words of my 3-year-old. Okay, so wait, just take a look at this. We're at 10 pounds, and look at the deformation here. I'm just going to get something to calibrate the amount of deflection we have. So look at that, at just 10 pounds, we have a drastic amount of deformation here. This is only supposed to go for 2 minutes, I thought. Okay, so we're at 30 pounds, oh, careful, 40. We are gonna slide it off the ends.
Oh, we broke it.
We broke it,
Hey.
Yes. 40 pounds. We broke 1/2 in depth at 40 pounds. So we were getting 240 pounds before, and half the depth, we didn't get 110 or 115, we got 40 pounds. That is a drastic reduction. So if we're going to take two of those and stack them on top of them, what we have is two beams that can take 40 pounds stacked on top of each other. We shouldn't get the same 230 plus 10 or 15 pounds. We should get somewhere around 80 pounds capacity for this one now. Okay, so this is two elements that have been cut down the length, or to cut the depth in half. So there is no glue between these laminations. You saw me just put them together here. So you can see that one of them worked and one of them didn't. So it's springy in between them.
So this is a load-sharing, non-composite.
Load-sharing, non-composite beam. All right. This really is my favorite lecture, people. I wish you could all be here. Or at least I could be there with you. I don't think the university would let me have you all here, even if it wasn't COVID. This doesn't seem to be. Okay, so we're predicting around 80 pounds. All right, we're past 40. We're at 50. Okay, slowly we're at 75, 80.
Now the theoretical should be half of the capacity of the full composite. So we could get up to 110.
Huh.
That last one was anomalously weak, actually.
Yeah, it really was.
Should have been a quarter of the, I would have thought.
Oh, I hear failure. We're at 110. 120, 100. We went up to 130.
We might be getting a bit of catenary.
Yeah, it does seem to be, doesn't it? We're at 140. Woo! 140. Okay. So
that is interesting, that it was more than 3 times the strength of the single.
But even more interesting is the same amount of wood from the solid versus 2 pieces stacked on top of each other was about half the load, which was about what it should be. So it's funny that just cutting it down the middle actually reduced its capacity versus cutting it down the middle of its width didn't change its capacity at all. We had pretty much the exact same capacity.
We might have had some amount of shear transfer across that interface
Just by
from
friction. It depended if there was a knot in there, anything along that line
That'd
could
push
make that
us up
happen.
above the half just a bit,
Yeah,
right?
yeah. But we were only just above the half mark, only just. And remember, all of these pieces of wood are visually graded and lots of buffers, and we use big reductions depending on how they're being used. So this one, my friends, we have those same 2 pieces, but this has been glued. We clamped it, we actually screwed it together and glued it, but then took the screws out so that the screws aren't doing anything. What we created was a shear transfer joint here. We've glued these together so longitudinal shear should not be an issue. This should be the same as one solid, where the same amount of area cut like this, not glued, was not as strong. Here's the thing, and we've consistently found this, because we have natural flaws within the wood, when we've done this in the past, we actually end up with a little bit of extra strength. It's going to be hard to tell because I think our scale isn't really showing past 110 pounds. It's almost like it's not going beyond, or a full loop plus 10 pounds. It doesn't really seem to show. But we have found that the gluing it's almost like it cuts through the flaws and then binds them by gluing. So we've actually found this to be consistently just a little bit stronger than the solid piece of the exact same dimensions.
Which is why glue lam is stronger than sawn lumber, right?
Exactly.
You make all the flaws discontinuous.
We're getting close to the end. We only have two more beams after this. 2 more beams after this. Okay, so we're expecting a full revolution. I think we're going to have to invest in a 2 kilonewton version of this.
Mm-hmm.
Do they sell them?
You can get a load cell, but this one is so nice and graphic.
I know.
This is a dairy scale.
We use this to test guards. That's how we originally came across it, to try to put a 1 kilonewton load on the top of a guard, which is really hard to do. Okay, so here we go. We're expecting a full revolution at least. We're at 150. We're we're at our full revolution now. Woo!
That was dramatic.
That one was an excellent
Hey, look
failure.
at that. That's a real tension failure, not
That is the kind of failure we're looking for right there. We got to a full revolution. We got to about 230 pounds. That is a beautiful wood failure right there. Catastrophic, which we don't love, but that is what we design for with wood. All right, so 230 for our composite action of 2 planks. So because Dave was feeling fancy when he got the saw out the other day, he decided...
Like I'm not always feeling fancy.
That's a good point. You're a fancy kind of guy. What we did is we decided to do that same thing, but with 3 planks instead. So we have 3 planks not glued, and then we're going to do 3 planks glued. What's your prediction for this failure without longitudinal shear transfer, Bowick?
I am predicting a springy failure on this one.
A springy failure.
I don't think we're going to get it to break. I think it's going to pull off the apparatus. It's going to deform so much.
We didn't even get a springy failure with our single ply. Oh, because it wasn't as strong. Yep, this has got some strength, but not a lot of stiffness. So, springy failure prediction from the big guy.
What's your prediction?
I think we're going to get it to fail.
You think we can break it?
I think we can break it. No, we're not. It's going to springy fail us. So,
I need a hard hat for this job.
okay, we're at 60 pounds. 70. Oh, that was a nice slow failure.
Great.
That was
ready?
excellent. Wait, I want to get a close up. You can still hear it creaking and cracking. You can see they're all failing individually. We're going to get a springy failure happening off to the side. All right, so I forgot to look at the scale. We were just... Let my camera settle down. We were just up over 70 pounds, I think, there. So 70 pounds.
You know what, Shannon?
What, David?
Capacity of 1/3 should be 1/3 squared, so 1/9. Each one should have 1/9 of the capacity of a full one. We had 3, which brings us up to 1/3 of the capacity of a solid, which was 210 pounds. Predicted failure, 70 pounds.
Well, it was 240, but pretty darn close.
Okay.
Okay, this one I left a screw in. Where's my drill? It's the wrong bit.
Oh, the screw's not
We're gonna. It's right in the middle. It's the one. It's not gonna do it. I just don't want it to land on you.
Oh.
It's right in the middle. Okay.
So-
So this is the same 3 plies, but glued together. So these have been glued together. So we should, in theory, see that 230.
Oh.
I guess that's the easier way to do it. The same 230 plus pounds.
Oh,
Did you break your ratchet strap?
I just jammed it. Okay, ready?
Wait. We're not. It's totally uncalibrated.
Well, you got a lot of load on there right now, right?
How much?
I don't know, 30 pounds maybe?
Well, it's at 220, so I think that is not the problem.
Okay. You want me to take the ratchet off?
Yeah. And at the, we might have broken our,
Broken this scale.
we might have broken the scale. Yeah, see? And that's the max calibration there.
So now we have to take the face off to move the hand.
Yeah. So we're starting minus 15 pounds. So I'll put 15 plus whatever we read on it because our scale is off.
Okay.
Okay. So we're at 140. We've gone up to 180. 200. You okay?
Yeah.
Did that screw almost nail you?
We are not insured for this. But that is a flexural failure.
Another great flexural failure. And it failed right at the point of loading, and that screw surprisingly almost hit me. Okay, so we can see that, guys. That was our 3 laminations. We got up to 200 pounds, or it was like, yeah, it was 210, I'd say, plus our 15, so 225. So we were pretty consistent across those solid pieces, whether they were laminated or not. I think we got good representation of the things we were expecting to see. You can go do your call. You just want to say bye to everyone?
All right.
Well,
Got to zoom.
Look,
Okay. Got to zoom. Bye, gang. Thanks for indulging us.
So where this is the last lecture, I'll probably do a little intro at the beginning of this so you guys would have already watched and you're thinking, oh, maybe I'll go inside and record it at the end. So I'm now going to go create a little spreadsheet or a fill-in chart for you guys. And I'm going to talk through some of the things we just learned with our data sheet in front of us. So you won't see this posted for a little bit. Again, why am I talking to you? You're watching it in real time. It's very unnerving doing this. I feel like I'm talking to you in real time, and then I have to remember you're watching it later. So I'll do my little summary and wrap up for you guys in a few minutes. So I'll do that now. Okay, here's our quick recap. So we had point loads at the midpoint of a beam spanning 5 feet with our pinned roller condition ends. So 5 feet is 1.524 meters. This is what our shear diagram would look like. This is what our moment diagram would look like with our maximum moment at the middle and our switch of shear happening at the middle. This is all stuff we derived last term, and you have these beam diagrams from the different beam loading tables. We went through and we tested 4 concrete beams. This is what your test sheets or your final assignment is going to be based on. So the answers are right here, right now. I am not going to upload this slideshow. You have to watch this lecture to get these answers. That's the only clause that I put in that final assignment. It's easy. You'll have the answers, but you have to watch the video to do it. So we had 4 concrete beams, CB 1 through 4, and we tested, the first 2 had 0 pounds, and then the last 2 were 120 and 115. We can convert those all into kilonewtons, just dividing by 225 pounds. And then we know that the shear at each end is half of that load. It's the same as me sitting in the middle of the table and half of my load going to each end. So we can find the shear values for both of those. And then moment, we know, is the force times the length divided by 4. We actually derived that last term too. So here we have our moment in kilonewton meters. So these are our concrete beam tests. Let's take a look at our steel beams. We had 6 different beams that we tested. We had failure loads that we measured, looking at the dairy scale. We can convert those into loads, into kilonewtons. We can convert those pounds into kilonewtons. We can then figure out what shear load these steel beams failed at. So we can figure out the shear loads that these failed at, and we can figure out the moment that they failed at. You can repeat these calculations if you want, so feel free to do that. And then the final test was our wood tests. We had 8 different beams that we tested. Here's the kind of makeup of what those all look like. You can compare this to the video if you would like. You can go back and watch this in the video. We tested these all to 240, 245, 240, 40 pounds, 140, 230, 70, and 235 pounds. We can convert those into kilonewtons, and then we know that half of that load gets distributed through each side of the beam, so we can calculate the shear load. And then we can figure out the moment that they failed at as well. So now we know the moment and shear that all of these failed at. So feel free to, based on this information, do that assignment that's uploaded to Quercus. You can keep rewatching this if you need to as well. Today's takeaway tip is that you guys are awesome. I can't imagine trying to do online school like this with the pressures that you guys have. I think architecture school is incredibly intense as it is, and trying to do it virtually, hats off to you guys. I've been super impressed with the quality of work and the communication and the diligence that you guys have had. So we're almost there. Your exam is on the 23rd. Sucks that it's at night. I begged them to change that, but they wouldn't do it. They had a different date for it that was horrible. That the same day your projects were all due, I communicated with the department, and they agreed that that was horrible. So they changed it to the 23rd, but they wouldn't change the time slot. So apologies, did what I could. And then your project is due on the 30th. And after that, you don't have to deal with me again unless you take my elective. It's been an honor, team, and thank you so much. All the best.